We're going to look at integrating using integral tables. There's lots of integral tables out there. If you have a math, a physics, and engineering book, they a lot of times have integral tables in the flaps of the book. There are also quite a few available online. There's a good one at integral-table.com, and I will post these links following this video. This integral table has an easy reference one if you want to print one out. It has most of the table on a single page here. Of course, it's kind of small because you could just get it printed on a page, but if you just want one printed out for reference, that's a good option. Then they also have them kind of broken down different places here, but if you scroll down just a little bit where it says contents, they have them sorted. So it's the integral table, but they've got them sorted by basic forms, rational functions, roots, logs, exponentials, trig functions, so forth. So it can kind of help you pick out a part of the integral table for whatever problem you're working on. So let's see how we would do this. Here we have the integral from 0 to 1 of tangent cubed pi x over 6 dx. Now a lot of times we have methods for dealing with these, and this one we have a method for dealing with this power on a tangent. We did that when we talked about the trig functions. However, it's quite a lengthy process, and depending on what you're doing, and maybe you're ready to use a table. So let's see how we would go about doing this. The first thing we would do would be to go to the integral table, and because it was a trig function, I'm going to go down to integrals with trig functions. And then as I'm looking at these integrals with trig functions, I see I've got sines, different powers of sines, cosines. Now I have products of sines and cosines. Okay, now I'm getting into the tangents. And I can see that number 90 on the table has a tangent cube. So there is the formula that I need. So if I go back to this problem, here is the formula that I need. The only thing I need to do is identify A. I can see that it then fits my form. A is pi over 6. So I can apply this formula, and I'm going to have 1 over pi over 6 natural log cosine pi over 6x plus 1 over 2 pi over 6 and secant squared pi over 6x, and this, because I have a definite integral, needs to be evaluated from 0 to 1. Let's see what we could do to simplify this a little bit. We can flip that over. That's going to be 6 over pi natural log. We'll go ahead and evaluate this as we go as well. Cosine, substituting in 1, we've got pi over 6 plus, simplifying this one, 3 over pi secant squared pi over 6, substituting in a 1. And then evaluating the lower limit, we'd have minus 6 over pi natural log cosine of 0 and minus 3 over pi secant squared of 0. Okay, so cosine of pi over 6, that's square root 3 over 2, so we've got 6 over pi natural log square root 3 over 2 plus, okay, secant squared pi over 6. Well, secant of pi over 6 is the reciprocal of cosine, so flip this over and have 2 over square root 3, but we need to square that. And we also have the 3 pi on the front, so flipped over and squared, that's going to be 4 over 3. And then minus cosine of 0 is 1, the natural log of 1 is 0, so that piece is gone. Here we have secant, secant's 1 over cosine, the cosine of 0 is 1, so this is going to be 1, square it, still 1, so we have 3 over pi. So then final answer, these would cancel here, and we have 6 over pi natural log square root 3 over 2 and 4 over pi minus 3 over pi, so that would be plus 1 over pi. Okay, let's look at another example, and in this one then, as I kind of look at the form of the integral, that's going to help me. And we could go to the integral dash table, but I'm going to go to a different one this time just to show you variety, and I will have these links posted at, so this one is found at Equation World. And it's just a little bit different way to present that. So this one has integrals with ax plus b, integrals with square root of ax plus b, and so forth. So you're kind of looking at the form, and as you go down here, Then it gets into the trig functions and the exponentials and the logs, so just kind of showing you different ideas. Now looking back here, we see that we have this in the denominator and it's got an x out in front and then the square root of ax plus b essentially. So let's go back and look. I had a square root involved in ax plus b. I'm going to click on that and see if I have one that has an x out in front. Here has an x, but it's in the numerator. I need it with an x down here in the denominator. So I'm going to scroll down here and there it is, number 4. I see this x out in front and then ax plus b, and it's got a couple of options here depending on what b is. So let's go ahead and go back and look at that. So here was our formula. So let's identify our pieces first of all. So we've got our a is right here, that's a 2. And our b is right here, that's -9. So in looking which of these I would use the second one because b is negative, and here if I put it in I'd have the square root of a negative. Here I'm doing the negative of negative b, so it's this second one that I use. So that's going to equal 2 over square root of -9, so that's going to be 9, and then inverse tangent of the square root of 2x minus 9, I'm just putting in the a and the b there, over -b, so that's going to be over 9. And then finally, to simplify that just a little bit, that's going to be 2/3, and then I'm going to have the inverse tangent of 1/3 square root 2x minus 9. But hold on, I'm missing something important, and I should have put it here as well. I need the plus c because this is an indefinite integral. They don't usually put that on the tables. They figure you would know that if you're doing an indefinite, put your plus c. If you're doing a definite, evaluate. So make sure you get that on there. Okay, let's look at another one. This one is x squared plus 6x. And in looking at this one, I sometimes want to do some algebra on these to get them in a form so I can find them on the table or be able to do something else with them. So I'm going to actually factor an x out here, and that would leave me the integral square root of x times x plus 6 dx. So there may be something on the table that involves a root, involves some x and some ax plus b, and that's what I'm going to look for. If that isn't the case, there's another option here to complete the square, make this a perfect square, and get something I can look up that had a x squared. But let's see first if we can find this. So I'm going to go back to the integral table. And looking at my choices, I'm going to choose integrals with roots. So as I look at these integrals with roots, none of these have the x times the other x. So now we're starting to get something that has an x, but I need everything underneath the radical, and then I had an x times ax plus b. So we're going to continue looking here, and ooh, this looked okay except the x is out in front of the radical. Oh, there's the one I'm after. It has an x and then an ax plus b. So here is the formula I can use to perform that integration. And so let's identify our pieces. Our a is going to be 1 and our b is going to be 6. And then we're ready to go ahead and use this. So this is going to equal 1 over 4. A was 1 to the 3 halves. And then we have multiplied by 2. A was 1 x plus b was 6, and then the square root of a was 1 x times x plus 6 minus b squared, so 6 squared times the natural log of a was 1 square root of x plus a was 1, so this is going to be the square root of x plus 6. And then of course we need our constant of integration. So let's see what we can do then to simplify this, and we've got it. So this is going to be 1/4 and then multiplied by 2x plus 6, and we can either leave this factored or we can multiply it back out. I think I'm going to go ahead and multiply it back out, kind of have it match the front one. First thing we started with, but doesn't matter. 36 natural log square root of x plus square root of x plus 6 plus a constant. All right, let's look at another one. Now this one, I have an e to the x and I have an e to the 2x. And if I go to the integral table and I have a look here, then I would think I'd want to go under integrals with exponentials. But as I look down through and I see these various integrals with exponentials, they involve e to the x or they involve e to the ax. But none of them have an e to the x and an e to the ax, which is what I had in my problem. So I'm actually going to need to do a little bit of algebra. So let's go back and have a look here. So the first thing I am going to do is I'm going to express this. I'm actually going to do a u substitution, and I'm going to let u equal e to the x, and then du would be e to the x dx. So I can express this as a du over square root of, and this is e to the x squared, so that's going to be u squared plus 4. So by doing that, I can now use a table. I also could use trig substitution on this because I see that denominator and that's just crying out to me. I could draw a triangle and do trig sub, but we're working with the integral table. So now let's go look on the integral table and see if we can find something that involves this square root of x squared plus a squared thing in the denominator. So I would go ahead and pick integrals with, it's a rational function, but it's also a root. So I'm looking here at the roots. I'm looking for a denominator that has an x squared. Okay, and here I have it because I had u squared plus 4. So this one would do it. And so I could express this as the natural log of u plus, and then here I would put what I had underneath. So let's go ahead and go back and do that. So this would be, I could express this as the natural log of the absolute value of u plus the square root of u squared plus 4, and then of course plus my constant of integration. Now I would need to resubstitute, so I have natural log of absolute value. I have e to the x plus the square root of e to the 2x plus 4 plus a constant. I see I won't need absolute value because that's always going to be positive. So there's my solution. Now sometimes an integral table is helpful. Sometimes it's easier to just calculate and not bother with going to an integral table. Sometimes it's even hard with an integral table, and we sometimes use a computer algebra system, and that's what we're going to look at next.